Hello, and welcome to the world of carbon nanotubes. Today we are going to be learning about the revolutionizing discovery of this new carbon structure and the reason behind their surprising instant fame among the scientific community. Carbon nanotubes were first discovered back in 1993 by Japanese physicist Sumio Ujima. Since their discovery, many scientists have worked together to unravel the secrets behind these wonderful carbon structures that seem to never stop surprising us with their versatility. Among the many interesting properties of carbon nanotubes, one of the most useful ones is the fact that they can take the role of a metal or a semiconductor. Metals are known for their electrical and thermal conductivity. We are all very familiar with how metals behave, but semiconductors are a bit more complicated to explain. Therefore, I will refer to the water pipe analogy, where electrons are represented by water and electron density is shown by the water level in the pipe. A metal in this analogy would have the same water level at both ends, or in other words, all electrons go through. An insulator, as we know, would simply stop all electrons from going through. And lastly, a semiconductor, which would be represented by a pipe that lowers the amount of water going through consistently. One amazing property about carbon nanotubes is their incredibly fast conductivity. Nowadays, we can direct electricity wherever we want using metal wires that serve as roads for electrons to travel. With carbon nanotubes, we can create nanowires that can achieve speeds several times faster than conventional wires. Certain kinds of carbon nanotubes act as electron highways. They form paths for electrons to travel that outperform any other kind of wire. On top of their incredibly high conductivity, scientists have confirmed they are officially stronger than steel, and of course, far lighter. This makes them one of the best materials for building nanostructures that are sure to withstand any possible application. It is not hard to believe why these structures are as strong as they are, for their atomic structure shares many similarities to that of diamonds. Like diamonds, they are only formed of carbon atoms that bond strongly together. But in reality, carbon nanotubes are more closely similar to graphene. Yes, the ink in your pencils, which is simply a one-dimensional hexagonal arrangement of carbon atoms. You can in fact form a carbon nanotube just by rolling up a single sheet of graphene, which is of course close to impossible, but in theory, their structure is that simple. The secret behind the wide variety of properties found in carbon nanotubes lies in the exact structure of each individual nanotube. The structure of all plausible carbon nanotubes can be obtained by the nanotube's chiral vector, which starts at the origin of a hexagonal grid and ends at a given coordinate point in the grid. This endpoint dictates the exact electronic, mechanic, chemical, optical, and thermal properties the nanotubes will have. But of course, we do not physically cut the desired chiral vector on a graphene sheet and roll them up to obtain the nanotubes we need. As mentioned earlier, this is complicated to do. Perhaps someday in the future we'll be able to do this, but for now we only have a couple of carbon nanotube synthesis methods, such as arc discharge, laser ablation, and chemical vapor deposition. Here at UOIT, we practice the synthesis method of chemical vapor deposition, which is similar to growing grass, though much faster. We start by vaporizing two chemicals, tyrosine, which contains the carbon atoms, and a catalyst which allows for the carbon nanotube structure to begin growing in a silicon wafer, which sits inside the furnace that reaches a temperature as high as 1,000 degrees Celsius. Once the nanotubes are done growing, we remove the silicon wafer, which is now covered in a forest of millions of carbon nanotubes. The nanotubes grown in the silicon wafer have different diameters and structures, and thus their properties can vary greatly from one another. One of the biggest hurdles in carbon nanotube technologies is the difficulty of separating all of these different nanotubes from each other. When it comes to application, companies need nanotubes with specific chiral vectors for their devices. This problem sparked a whole new science in the field of carbon nanotubes, which is the separation and characterization of individual nanotubes. Separation techniques are complicated but fascinating. Finding a way to separate carbon nanotubes by specific chirality in bulk is considered to be the biggest breakthrough in the field today. The success of carbon nanotubes lies solely in finding a good separation technique. Thus, big companies such as IBM are gathering the best scientists in the field to develop a separation method that will allow them to sell specific nanotubes to the companies in need. In UIT, we have worked with the separation technique of gel chromatography, which uses a surfactant that's similar to hand soap and cases molecules of certain diameters. By using different gels, we can trap different sized carbon nanotubes, giving us the opportunity to separate particular nanotubes, but not all nanotubes we need. Perfecting separation techniques will bring about an exciting new future. Who knows what kind of technologies will inevitably arise from this breakthrough, but for now we can only theorize nanomachines based on the properties we have discovered about each individual nanotube. Such machines might revolutionize devices such as computers, solar cells, medical equipment, and many other technologies involved in the nano world. There sure is a bright future in this world with carbon nanotubes, but for now, we will keep working hard to bring the future to us sooner.